So I'm Jeff Hollinger at Oregon State University, and I'm going to talk about information gathering with multi-robot teams, and also looking at the role of the human. So this actually combines elements that we saw in the first two talks, Gaurav's and Mark's talk, and we're also going to be talking about some other issues that we're dealing with as well in terms of resilience for these kinds of teams. So bringing us back into the water, the motivation here is similar to what Gaurav discussed, where we're trying to develop systems that can do information gathering, reconnaissance, monitoring in underwater environments. This is an animation of the Oregon State glider, so Gaurav already went over the specifics of those vehicles, so I won't do that again. What we'd like to be able to do is field multi-robot systems for this kind of vehicle and also propeller-driven vehicles. They can do things like monitor harmful algae blooms, inspect offshore facilities or shipping activity, and also for ecological sustainability, try to understand what's going on out in the ocean. But specifically, the problem that I'm going to be looking at today is scaling up this kind of multi-robot exploration. So if we have information gatherers that form a heterogeneous team, this could consist of multiple different types of vehicles, including human operators. When we want to be able to perform tasks like mapping, search, exploration, and reconnaissance, then there are a couple of issues that haven't been discussed yet that I wanted to deal with here and present some preliminary solutions for. So the idea is that in these kinds of scenarios, each vehicle is making its own observations, and other vehicles are concurrently making observations, and then there's one or more human that oversees the mission, and those humans might be playing a command role. They may not be in the field, or they may be in the field with the vehicles gathering information on their own. So at a given moment, a robot has various different options. They can move to sense the environment themselves with their sensors. They could ask other robot team members for information, and maybe those team members have been gathering information with heterogeneous sensors, or they could even potentially query a human for high-level guidance or other information. And so in order to figure out how to trade off between these different kinds of events or these different kinds of actions, what I would argue that we need is to be able to predict the value of information. So I need to be able to predict what kind of information am I going to get from a teammate, or from my sensors, or from the human team member, and I need to be able to predict what's the value of that in order to figure out what I should do next. And in some cases, there's a cost associated with communication, saying that the vehicle needs to surface to get into a better communication mode or move closer to that teammate. So how do I trade off between these different kinds of modalities? And so ultimately, what we want to think about here and what we're moving towards, and I don't have all the answers on how to do this, is how to move from kind of the current state of practice where we have multiple humans in the command center. If you think kind of the recent DARPA challenge, we have a bunch of humans that are controlling the vehicle together. We like to move towards situations where maybe we have a command, someone in the command center and then someone on the field. Just call this a responder, but it could be a soldier or even a scientist for different applications. And then we have multiple vehicles being controlled by these kinds of human teams, and then ultimately heterogeneous vehicles, or different sub-teams of heterogeneous vehicles that are communicating with each other, and then also communicating with the humans in the field and in the command center. And so let's start by sort of teasing this apart and thinking about how do we do robot-to-robot queries, how do the robots decide how to communicate with each other, and then also how do we do robot-to-human queries. So first, thinking about robot-to-robot queries, let's talk about one specific problem domain so we can flush this out. So if I have multiple robots that are autonomously locating a target, similar application to what Mark was discussing earlier, these vehicles have noisy heterogeneous sensors, which fits in with some of the themes of the workshop. Communication here, inspired by this underwater domain, if the vehicles are at the surface, they can communicate freely, but if they're underwater, they have very limited communication. But they can potentially send a few bits to request another vehicle to surface and then share information. And so in order to figure out how to act in this kind of a situation, we need to be able to reason about the kinds of information that we can get and how we might be able to get that. So just giving a visualization for this particular domain, we're trying to develop frameworks that are more general across problem domains, but here we'll just talk about this one in particular. If I have a target here, if I'm within some range of the target, it's highly likely I'm going to be getting positive readings that there's a target there. If I'm away from the target, I'm probably going to get negative readings, but there's also the possibility of a false positive and a false negative. And so this is the kind of scenario that we're thinking about. We have multiple vehicles all gathering information, trying to locate this target. So back to this idea of the value of information, one of the challenges is to decide when to communicate. So if I have, this is the map that AUV1 has, this AUV2 has, and this is the map that AUV3 has. This underwater vehicle has not identified any targets, but these vehicles have identified a number of possible target locations. So there's actually a fairly high value for the second AUV and the third AUV to share information and then get a much better idea that actually, this area here is where we should really go search and we should go to distribute our effort. So how do we figure out that this is a worthwhile thing to do, that's a communication action that should happen? Well, before we get there, let's also talk about this idea of multiple vehicles and heterogeneous sensor output. So in this particular domain, a high-quality sensor has a very sort of step function-like distribution, very likely to get positive results if it's near the target, very likely to get negative results if it's not, and then we also can have lower quality sensors, and so we need to be able to take that into account when we're thinking about these value of information models. Now, what we do is we create a graphical model here where observations are taken in a particular location of an unobserved target location. We never observe that target location exactly. And then we have M vehicles taking these observations. So the idea being that each vehicle automatically gets access to its own observations, but in order to get observations from other vehicles, it needs to make that expensive query. And so in order to figure out what the value of information of getting those additional observations are, we want to be able to develop a framework for thinking about that. So ultimately, we want to constrain the estimate of the target's location. We want to think about which observations are the most valuable. And the way we do that is by using the expected KL divergence. So the idea behind this is that if I can predict what kind of distribution I will have after I've received that new information, and figure out how different that distribution is from my current distribution, then that's going to give me some level of informativeness. Now in this particular search domain, this is a good metric because different distributions mean that there's more information, but in other domains you might need to tailor different metrics for this, and this is something that we're working on. But the expected KL divergence is basically saying that summing over the possible measurements I might receive, and this can be tricky, but we'll talk about it in the next slide, I need to be able to predict the difference between the distribution that I'll have once I have that measurement and the distribution that I currently have. And so in order to do this, we need to make a few assumptions on basically on the measurements. So if we assume they're conditionally independent, then we can actually calculate this expected KL divergence fairly efficiently by using Monte Carlo sampling. For Gaussian distributions, this is definitely a reasonable thing to do. For more complex distributions, you need to use Markov chain Monte Carlo, but you can still do it. So ultimately, what you do is you sample the prior, which is where you thought the target was, and then you do this sort of importance sampling approach based on all of the different measurements that you might be able to receive from your teammates, based on whatever knowledge you have of their location or any other information that you have available. And so that's nice because it gives us an estimate of what our KL divergence is, and it also gives us some guarantees on what the variance of that estimate is. So what does this look like in this domain? So here we see kind of a prior target estimate. This vehicle has flown from here through this target. You can think about this in terms of underwater vehicles or even aerial vehicles if you like. And then you see there's a potential target up here that's actually the true target location, and then also one down here. The probability of a true measurement is not actually particularly informative because if I continue to get true measurements here, that's not going to further constrain the location of the target with this particular sensor modality. If I think about the KL divergence, then this actually gives me a really interesting topography of where I should go to sense. So I actually want to sense up here, which will collapse this mode here, which is a false mode, or I want to sense here, which will also collapse this mode and tell us where the true target location is. So let's take a look at this. So here's with a single vehicle. It's not quite as interesting. It basically finds the target, and then it kind of does this circling behavior where it refines that location. It's kind of what you expect, just as a sanity check. But the more interesting case is the multi-vehicle case, and that's the case where the vehicles can query for information. So here we have two vehicles trying to locate a target up in that top left corner. Here you see that the left vehicle, which has a noisier sensor than the right vehicle, sorry, the way around. The right vehicle has a noisier sensor, detects a false positive, and that's sufficiently different based on a threshold that the left vehicle now requests that information, and so now they have a fused observation of where the target is. Now the right vehicle now actually collapses that false mode. The left vehicle finds the true target location, and they still haven't actually shared information again, but here they're now cooperatively locating that true target location without communicating. They'd only communicated once in this entire time. And so here they do a final communication run, and the target is now very well localized. And this was done with only 2 communication events over the course of the entire mission. So this is a pretty interesting preliminary result here, showing that we can use these kinds of value of information approaches to do a better job of cooperative localization. But that's only about half the story. We want to also think about the role of the human, the mission commander, or the first responder in these types of scenarios. And so now let's think about how can we do human-robot teams in human-robot coordination. And so in order to do this, I'm going to have to shift domain slightly, because there wasn't a human in the previous domain. But here let's think about a domain that's more similar to the kind of things that Gaurav was talking about, where I have a robot that's operating in an area like this, where we have some areas with high threat. So those are areas where the vehicle does not want to go, and some areas of high interest. So those are the areas where the vehicle does want to go. And then we have disturbances, which are in the form of ocean currents in this case, so again, for the underwater monitoring domain. And so what I want to be able to do is I want to be able to balance risk or threat with information quality, which are essentially the areas that I want to go to. And then I have some uncertainty, and here I have a human operator that's going to provide me with high-level guidance and preferences in terms of the types of trajectories that the team wants to execute. And this human can tell me, oh, I really prefer you to avoid this amount of risk to get this amount of information. There's kind of a preference trade-off that goes on there. So the optimization framework that we use to do this is we want to find some optimized trajectory, given an initial trajectory provided by an operator, and given some risk functions. So those are sort of the threat of being in a particular area, and then also a deviation function that tells me how much my trajectory has deviated from that, the one provided by the human operator. So I'm trying to minimize this weighting of the deviation from what the human originally wanted, and then the risk of the trajectory, which is something that the human might not have access to, or the human might not necessarily be able to predict based on their knowledge. And then there's also this weighting parameter that tells me how much do I care about risk versus deviation, and that's something that can be changed on the fly. So how do we optimize something within this framework? So if I can calculate my deviation and risk, I can do iterative optimization here, similar to a Markov decision process, where I have a state action pair that tells me, here's the current state that the robot's in, here's the action that it can take, these are the state transitions with an uncertainty, so that's based on the ocean currents, and then I can think about the difference in deviation or the difference in risk by making those changes. And so ultimately the output here is the long-term cost for each state action pair, and then I can read the optimal solution based on both the human input and the original input from the team. So what does this look like? So here in this ocean monitoring domain, I have my threat map or my risk map, and so this is the trajectory that the human initially provided here in green, and then using this framework we can refine those waypoints and get the red trajectory that avoids those risky areas. We can also sort of trade off between risk and reward by adjusting that one particular parameter, and that gives us waypoints that move from sort of the risky areas to the less risky areas. This also accounts for uncertainty in the ocean currents. And so this is something that we could do with a single vehicle or with multiple vehicles if we're planning multiple trajectories, once we have that operator preference learned based on that initial framework. So how does this fit in with the idea of the value of information? So I haven't really talked about the connection there. And so the way that we can incorporate value of information here is by thinking about what's the value of asking for the operator's preferences. Maybe I got an initial trajectory, I refined it somewhat, but I still don't have a good idea of which types of plans or which types of trajectories the human member of the team would actually prefer. And so what I can do is I can model the level of uncertainty in the human's preferences using a Bayesian inference type method. So this could be something like a Gaussian process. You could also think about the expected KL divergence like we were thinking about in the multi-robot search domain. And so if I have this space of kind of distance versus information, and I think about preferred plans in here and not so preferred plans in here, and I can also think about, well, if I show a human a plan, or I ask for a demonstration of a plan, what are the best kinds of plans that I could show them or ask them to rate, rank, or provide in kind of a learning from demonstration framework? And what we see is that by taking into account the value of information, we actually can present the human member of the team far fewer trajectories. So only, with only a handful of trajectories, we can get similar rating errors as we would if we were giving them a large number of trajectories. And what this has the potential to do is it has the potential to really reduce the cognitive load and reduce the effort from the human operator when they're a member of these multi-robot teams. So we haven't gotten the human-robot element working on a multi-robot team yet. But we do have some results with a single robot, and so this is Pudding Stone Reservoir, and this is in collaboration with Gaurav as well. And so the goal here is the vehicle wants to track some depth or temperature of interest, but it's not sure which depth or temperature is particularly interesting. That's something it has to query the human for. And this is a propeller-driven vehicle, so it doesn't have the duration or the scope of some of the glider vehicles, but it kind of provides a surrogate in this domain. And so what we're doing is it's monitoring this lake, it's getting things like depth, temperature, salinity, and it's trying to figure out what's the right area to monitor that's going to satisfy the human command, the human mission commander. So here we have kind of this utility map. So this is based on kind of the estimated high impact areas. So the human provided this trajectory here, which you can kind of see in black. That basically follows this utility contour, and this was not known before, this was learned from that trajectory. And then what the system does is it takes that presented trajectory and it refines it so that it actually does a better job of tracking this utility contour. And so here you see it's actually able to monitor this entire caldera here and actually do a better job of estimating that, basically monitoring that utility than it would have with just the human operator's trajectory, given basically sort of more waypoints that provide better monitoring quality. So essentially what we've done here is we've talked about this idea of general value of information. So we've talked about the robot-to-robot queries in that search domain, where we're using that expectation of the KL divergence to predict the value of teammates' knowledge. And what this allows us to do is it allows us to trade off between communication and sensing. And then we also talked about robot-to-human queries, where we're modeling the certainty in a human's preferences using a similar framework, and then actively querying for additional information when necessary. And so the key idea here that I really want to try to push is this idea that we can treat sensing, communication, and human-robot interaction within a common framework. And then the main question is, how do we develop the metrics and the optimization functions that we need in order to basically develop that value of information and do that proper trade-off. So a few just sort of discussion points and areas of ongoing research. So I've certainly alluded to this before, that we want to think about general alternatives to the KL divergence. Now, KL divergence works well in that search domain, but in other domains we might need more sophisticated metrics that better relate to the actual optimization quantity for things like reconnaissance or tracking or those kinds of things. And so a lot of times this is going to require calculating an expensive expectation over measurements. So I think there's a lot of work to do in trying to do those things efficiently. Heterogeneity, we touched on that a bit. Thinking about different sensor models, or if the team members don't know the other team member's sensor models exactly, then that's something that we need to be able to incorporate. Also resilience, which is certainly coming up in the workshop a lot. If team members fail, then how do I decide what information is lost by that failed team member? I think that's a very interesting question to ask. And then another really interesting thing to think about is, if I request a teammate to surface and communicate with me, but the teammate doesn't do that, then I can actually infer something from that. Either I can infer that that teammate has failed or is not actually acting properly, or I can potentially infer that that teammate doesn't think it's a good idea to surface and communicate with me. So is there a way to infer information and incorporate that into the framework? And then, of course, the role of the human. I haven't talked at all about having a human in the field and gathering information with the team, but that's something we're also working on incorporating. So with that, I'll thank ONR and NSF for the funding, and my postdoc and PhD student who worked on this work, and thank you for your attention.